Our second unit this semester was talking about derivatives. We talked about an introduction to derivatives. We began by discussing the difference between average rate of change and instantaneous rate of change. Average rate of change is something you guys have been able to do since before calculus, where you plug in an x value like 0, you plug in an x value like 2, and then we find the slope between those 2 points. Instantaneous rate of change is where calculus comes in, when you actually have to find how quickly something is changing at an instant. Hence the word instantaneous. And that's where derivatives came into play. So we talked about a couple different things that relate to derivatives and how they're similar to each other. We said that the slope of the tangent line is another way of talking about the derivative. The instantaneous rate of change, how quickly something is changing at an instant. This was the definition of the derivative, or at least one of them. We talked about the different notations, like y prime. We would talk about dy dx, and then f prime. We went forward from there and we spent some time actually calculating derivatives by hand. We only did this for about 4 days, and it was a little lengthy, where you actually use the difference quotient in order to calculate it. There are a couple problems in the review where you'll see the difference quotient set up, and we'll talk about those in just a minute. But never really on the AP test will they force you to use the difference quotient in order to evaluate or to know the definition of the derivative. So we'll talk about the ways around that, I guess you could say. One of the things I want to mention from this section, however, is about writing the equation of the tangent line. Remember, in order to write the equation of a tangent line, we need 2 things. We need a point and a slope. They give us half of a point in 2. To find the other half, we would plug 2 back into the original function. So 9 minus 2 squared would be 9 minus 4, which is 5. So our point would be 2 comma 5. And in the derivative, if you took it the long way, you could go ahead and do that. Or the shortcut way would be the derivative of this is negative 2x. If we plug 2 into that, we get negative 4. So our derivative is negative 4, our slope of our tangent line is negative 4, and the point is 2 comma 5. So we could use that to write the equation of the line as y minus y1 equals m times x minus x1, and that's point slope form. From there, we went into talking about differentiability. We said that a function is differentiable as long as it is continuous, and if the left and right hand derivatives exist, and they have to be equal. The layman's term definition we said was if a train could ride along it without derailing, then it would be differentiable. So here were some examples of things that were not differentiable. So a corner when it has a sharp turn, a cusp like this, a vertical tangent line, or a discontinuity. These are the 4 examples where a function would fail to be differentiable. Then we got into some basic derivative rules, so I'll kind of skim through this presentation really quick just to talk about it. Remember the power rule that just says x to the power of n, bring down the exponent and lower the exponent by 1. So there were some examples we did with that. This was all power rule, just different ways. If we're adding things together, you just take the derivative of each term individually. For this one, we had not yet at this point used the product rule or learned the product rule. For this one, we had not yet learned the chain rule, so you would have had to multiply those out and then taken the derivative. But now that we know the product rule and chain rule, we could have used those instead for these ones. Remember that if it's a number or a variable, in the denominator, just to bring it up to the top as x to the negative 1 before you take its derivative. So that applies to all of these. If it's a square root, remember we can rewrite with a fractional exponent like x to the 1/2. What else did we have here? Same thing, if it's in the denominator and a fractional exponent, make sure to take that into consideration. I think there was some like that on your review. Calculus in the calculator, we started learning about the calculator. Remember that horizontal tangent lines occur wherever the derivative is equal to 0. So if we were going to go ahead and find the derivative of this function and then use our calculator to graph the derivative, if we found wherever the derivative was equal to 0, we would say that it has a horizontal tangent line. At this point, we started talking about differentiability of piecewise functions. So in order for a piecewise function to be differentiable, and this is almost guaranteed to be on the test, so I'm going to kind of go through this one a little bit slower. In order for a piecewise function to be differentiable, it has to be continuous, and then if it is continuous, we have to find the derivative to see if the derivative has its left and right hand limits equal to each other. So first things first, if we plug 1 into this function, we get 1 squared plus 1, which is 2. If we plug 1 in here, we get 2 times 1, which is 2. So yes, it is continuous, so we can go ahead and test for differentiability. In order to take the derivative of the top, we would get 2x. If we take the derivative of the bottom, we just get 2. If I plug 1 into the derivative of the top, I get 2. If I plug 1 into the derivative of the bottom, I also get 2. So yes, this function was continuous and it was differentiable. Therefore, we can say this function is differentiable at the breaking point. But you have to test both of those. You can't make the assumption that one is true over the other. You have to test continuity and differentiability every single time with piecewise functions if it's asking about differentiability. We also did some examples where it was forcing differentiability. So in this example, we would have to first force it to be continuous. So plug 1 into x in the first and second equation and set those equal to each other. But you'll realize that you still have a's and b's in your equation when you do that. So then you have to take the derivative of both of these and substitute 1 in again and set them equal to each other so that you can force it to be continuous and differentiable. That's how you're going to solve for both a and b in order to make this function continuous and differentiable at 1. After that, we got into the product rule, and we talked about how the product rule is the derivative of the first times the second, plus the first times the derivative of the second. So we learned how to do a problem like this using the product rule. When I had you guys set it up, I had you set it up something similar to this, where we did u prime times v and then v prime times u. Don't forget that when we do product rule, we add them. Then we talked about quotient rule. When we're dividing two things, it's the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. And then when I had you guys doing it, it looked like this. So it was u prime times v again, v prime times u again. This time we're subtracting in between them though, and then all over the bottom squared for quotient rule. After that, we talked about the trig derivative rules and the transcendental derivative rules. So we wrote down our derivatives for sine, cosine, tangent, cotangent, secant, cosecant. Remember, if you're trying to remember them, sine, tangent, and secant do not have negatives. Cosine, cotangent, and cosecant, the ones that start with co, and co, are all negative. And then secant and cosecant are both secant tangent and cosecant cotangent respectively, and then tangent is secant squared, cotangent is cosecant squared. So kind of the cos go together and the negative for all the cos go together, etc., etc. Anyway, find a way to kind of organize that in your brain and put it to memory. And then we had the transcendental derivative rule, so the derivative of the natural log being 1 over x, the derivative of e to the x was e to the x, and then last but not least, the one that's not used very frequently, but every once in a while comes up, the derivative of a to the x is a to the x times ln of a. All right, so now let's look at some of the questions from the review packet. There are quite a few that relate to derivatives, so we'll go ahead and kind of hurry on through these ones. First things first, when we're taking derivative at 4, but we have square roots, I would rewrite this as x to the 1/2 plus 3x to the negative 1/2. If you're going to bring up that one from the bottom, it's a negative, and then both of them to the power of 1/2. So if we go ahead and take the derivative now, that would be f prime of x is equal to, for the first one, that would be 1/2 x to the negative 1/2. For the second one, that would be negative 3/2 x to the negative 3/2, because when I subtract negative 1/2 minus 1, negative 3/2 x to the negative 3/2. Negative 1/2 minus 1 is negative 3/2. So now I can evaluate at 4. If I plug 4 into this function, I get 1 over 2 square root of 4, because x to the negative 1/2 gets pushed back to the bottom underneath the square root, minus 3 over 2 square root of 4, but then that's to the power of 3. So this is 4 to the root 2, but power 3. That's where this comes from, root 2 and power 3. So the square root of 4 is 2. This is 1 over 2 times 2, minus 3 over 2 times, the square root of 4 is 2, but then 2 cubed is 8. So this is 1 over 4 minus 3 over 16. If I get a common denominator of 16, this would be 4 over 16 minus 3 over 16, which is 1 over 16. Answer choice A. Number 2, this one probably could have been in the last video, but that's okay. Let f be a function defined above where c is constant. For what value of c, if any, is f continuous at x equals 2? So if I plug 2 into the top function and the bottom function from the left and right, and we force them to equal each other, we would get 2 squared, which is 4, sine of 2 pi, equals, if I plug 2 in here, that's 2 squared, which is 4, plus 2c minus 18. Sine of 2 pi. Well, sine of 2 pi is equal to 0. So that would be 4 times 0 is 0 equals, on this side, 4 minus 18 is negative 14 plus 2c. Add the 14 over, so we get 14 equals 2c, and then divide by 2. So c is equal to 7. So that's the value that's going to make that function continuous. Number 5. They want to know dy dx evaluated at x equals pi over 3. I have sine of x times cosine of x. That's going to be a product rule. So u equals sine of x, v equals cosine of x, u prime equals cosine of x, v prime equals negative sine of x. If I multiply backwards first, cosine times cosine is cosine squared. Multiplying forwards and adding them, I get negative sine squared. If I plug in pi over 3, I get cosine squared of pi over 3 minus sine squared of pi over 3. Well, cosine of pi over 3 is 1/2, so this is 1/2 squared, which is 1/4, and sine of pi over 3 is radical 3 over 2. If I square radical 3 over 2, I get 3 over 4. If I subtract those, I get negative 2 over 4, which is negative 1/2. Answer choice A. The next one, number 9. Again, this one probably could have been in the last video, but I didn't see it earlier. It says, here's a function called f. If the line y equals b is a horizontal asymptote to the function, then b equals blank. So remember that a horizontal asymptote is the limit as x approaches infinity. So I'm looking for the degree of the top and the degree of the bottom. So if I look at just the leading terms, in the numerator I have a 2x and an x. If I multiply those out, I would get 2x squared. I don't really care about what happens to the rest of the terms because I just know that's my leading term. On the bottom, I have x that's being squared, so x squared would just be x squared. Since the degree of the top is 2 and the degree of the bottom is 2, that means I have a horizontal asymptote at the ratio of the leading coefficients. So in this case, that would be 2 over 1, which is 2. Answer choice C. Number 11. For number 11, we have a function defined above, which is a piecewise function. Which of the following statements are true? The first one says, does the limit as x approaches 1 from the left equal the limit as x approaches 1 from the right? So if I look at 1 in the original function, in the first function from the left, 3 times 1 is 3. 3 minus 2 is 1, so the limit from the left is 1. If I plug 1 into the second function, 3 times 1 is 3, minus 2 is 1, but ln of 1 equals 0. So the limit from the left equals 1, the limit from the right equals 0. So no, that's not true. For the second part, if I take the derivative, they want to know if the derivative from the left and right are equal. Well, f prime of x, the derivative of the top function is 3. The derivative of the bottom function, well, technically we haven't reviewed the chain rule yet, but you guys know how to use the chain rule. So this one technically shouldn't have been in this video, but that's okay. The derivative of this using the chain rule would be the derivative of the outside. So the derivative of the natural log is 1 over whatever is inside of the natural log, 3x minus 2, times the derivative of the inside. So 3x minus 2 has a derivative of 3. If I reevaluate the limits at 1 on the first part, there's nowhere to plug in 1, so that's just 3. On this one, if I have 3 times 1, that's 3 over... If I plug in 1 to the denominator, I get 1, which is just 3. So yeah, the limit from the left and the limit from the right are both 3. So that is a true statement. The third one is not true, however. The function is not differentiable. The reason it's not differentiable is because the function is not continuous. That first one was false. And remember, if the function is not continuous, then automatically we know it's not differentiable. So the only one that's true is that second option. Number 14. On this one, this is one of the definition of the derivative problems, but I'll show you that there are multiple ways to do it. So h equaling 0 for this one would be sine of pi over 3 plus 0, which is just sine of pi over 3, minus sine of pi over 3, which is 0 on the top. And then if I plug 0 into the bottom, I also get 0. So L'Hopital's rule does work here if you wanted to use L'Hopital's rule. However, there's a problem we're going to look at in just a minute that's very similar to this one, so I'm actually going to use L'Hopital's rule for that one instead. I'll show you this one using the definition of the derivative. Remember that the definition of the derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. So the other way to do this, besides using L'Hopital's rule, is to be able to recognize that this is in that format. In identifying, I want to identify what f of x is, and I want to identify what a value I'm trying to evaluate the limit at. So in this case, the function itself is sine of something. Notice that we're plugging that x plus h in here, and we're plugging that x plus h in here. So it's sine of x, and then the a value I'm trying to evaluate it at is pi over 3. And you'll notice if I use that and plug it into the definition of the derivative, I'll get what I started with originally. So this is essentially saying, since it's the definition of the derivative, it's essentially saying what is the derivative of this function, and then once you found that derivative, evaluate it at this a value. So the derivative of sine of x is cosine of x, and the derivative evaluated at pi over 3, cosine of pi over 3, is 1/2. So the answer is B. Like I said, I'll show you how to do it that other way using L'Hopital's rule in that next example that we have. All right, number 17. Number 17, they want the derivative evaluated at 2. Cool. The derivative of this first piece right here would be negative 8x to the negative 3, since negative 2 minus 1 is negative 3. Right here we have 1/4 times 2, which is 1/2 x to the first power, and then the derivative of 4 is 0. If I evaluate this at 2, I'm going to get negative 8, 2 to the negative 3, plus 1 over 2 times 2. Well, 2 to the negative 3 means we're going to take that and put that back on the bottom of the fraction. So that's negative 8 over 8, because remember, negative exponents move things to the bottom. Plus 1/2 times 2 is 1. Negative 8 over 8 is negative 1, plus 1, this is 0. Answer choice D. Number 22. 22 is a quotient rule problem. The top is x plus 1. The bottom is x squared plus 1. U prime is 1. V prime is 2x. If I multiply backwards first, that would be x squared plus 1 minus, since this is quotient rule, multiply forwards. That would be 2x squared if I'm distributing, 2x squared, and then don't forget to also distribute the negative. So you can either group this and then not distribute the negative, or you can distribute the negative now. So 2x times x is 2x squared, and we're subtracting. 2x times 1 is 2x, but since I have that negative that's distributed to both of them, this should also be a subtraction. All over the bottom squared, so that's x squared plus 1, quantity squared. If I simplify what's in the numerator, I have x squared minus 2x squared, that's negative x squared, minus 2x, and then plus 1, all over x squared plus 1, quantity squared. That's answer choice B. Notice, by the way, that... Oh, no, it's not. I apologize. That's answer choice C. X squared plus 1, quantity squared. I thought maybe they were going to trip us up with the minus and plus, which it looks like they kind of did here, but not quite. So anyway, hopefully, if you did forget to distribute that negative here, you would have found your mistake before you selected an answer. Number 24. All right, number 24 was that other example of the definition of the derivative that we could use. So again, this one you could use as the definition of the derivative. The function itself is the natural log. The value we're trying to evaluate at is 3. But I'm going to go ahead and instead of using the definition of the derivative, I am going to use L'Hopital's rule. So if I plug in 2 here, I get ln of 2 plus 3, which is 5. ln of 5 minus ln of 5 is 0, and then if I plug 2 into the bottom, I also get 0. So yes, L'Hopital's rule does work here. Multiple choice, you wouldn't have to note that, but I just put it because I know for free response we do. So L'Hopital's rule says to take the derivative of the top. The derivative of ln of x plus 3 would be 1 over x plus 3 times the derivative of the inside. Well, the derivative of x plus 3 is just 1, so times 1 doesn't change anything. ln of 5 is a constant. The derivative of a constant is 0, so this is the entire derivative of the top. And then the derivative of the bottom, which is x minus 2, would just be 1. Derivative of x is 1. If I evaluated 2 now, plugging in 2 now, I would get 1 over 2 plus 3, which is 1 over 5. So that's an alternate way of doing this problem. Rather than identifying the function and the value being plugged in, you could just use L'Hopital's rule to simplify. 29. Number 29 says, if f is the function defined above, then f prime of negative 1 is blank. So first, because this is a piecewise function, let's make sure it's continuous, because if it's not continuous, then the derivative does not exist. So if I plug negative 1 into the top half, I get 3 times negative 1 is negative 3, plus 5 is 2. If I plug negative 1 into the bottom half, I get negative 1 squared would be negative 1 plus 3, that's also 2. So it is continuous. Let's go ahead and take the derivative now. f prime of x would be, for that first top function, would be 3. For the bottom function, it would be negative 2x. If I plug in negative 1 to both of these, plugging in negative 1 to the top gives me 3. Plugging negative 1 into the bottom gives me negative 2. Well, since the derivatives are not equal to each other, we would say the derivative does not exist. Therefore, it's non-existent. Number 2 in the calculator section. So now we're in that second half of the calculator section. This is more of a conceptual type of a question, but it does apply here. It says if the graph of the second derivative of some function f is a line of slope 6, a line of slope 6. So let's think about that. A second derivative is a line and has a slope, negative 6. It has a slope of negative 6. So I'm just going to draw a line with a slope of negative 6. Now keep in mind, this is the second derivative. This is f double prime. So let's make sure we read this correctly one more time. The second derivative of a function is a line of slope negative 6. So here's a line, slope negative 6. Then f would be which type of function? So keep in mind, this is kind of more of a conceptual question, but I think you guys are okay with understanding where it comes from. If the second derivative is a line, that means that the first derivative must have been a quadratic. Let's talk about why. If this is a linear function, let's just say this is the line y equals negative 6x. If this is the second derivative, y double prime equals negative 6x, this one had to have been a quadratic. For example, maybe it was 3x squared or even negative 3x squared. Because if you take the derivative of this, the derivative of negative 3x squared, bring down the 2, you get negative 6x, which is where we got that from. So the first derivative had to have been a quadratic so that when you took its derivative, it was linear. Well, they don't want to know about f prime, they want to know about f. So going back one more, the original function must have been a cubic. All right, the original function must have been a cubic. For example, if the original function was negative x cubed, its derivative, negative 3x squared, and its derivative, negative 6x. So the original function had to be cubic in order to have a derivative that was quadratic and a second derivative that was linear. So D is the correct answer. Number 3 is a quotient rule because it's f of x divided by g of x, and we're using this table of values. So if I'm going to set up my u and my v, the top function is f of x, the bottom function is g of x, u prime is f prime of x, and v prime is g prime of x. Now I'm going to go ahead and evaluate what these numbers are right now. If I'm plugging in 0, I want to know what f of 0 is. So f of 0 is 3, g of 0 is 2, f prime of 0 is 4, and g prime of 0 is pi. So now if I go forward with the quotient rule, I'm going to multiply backwards. 4 times 2 is 8, minus, multiply forwards, 3 times pi is 3 pi, divided by the bottom squared. So the bottom is going to be that 2, 2 squared is 4. So we have 8 minus 3 pi over 4. Answer choice A. Notice that this is also an answer if you had accidentally put it in the wrong order, so be careful with the order. It's backwards then forwards. All right, no questions on that one. Let's look at number 9. Number 9 says the limit as x approaches a equals f of a, then which of the following statements about f must be true? Remember that we talked about this as the definition of continuity. We talked about this earlier in the video, so I know A is a true answer. Remember, in order for something to be continuous, the limit has to exist, the function has to exist, and they have to be equal to each other. So that is literally the definition of continuity. Just to read through the others to make sure we understand why they're not necessarily true. In order for a function to be differentiable, the derivative limits have to exist from the left and right. So that's not necessarily true from what we have here. For part C, f of x equals f of a. For all values of x, f of x equals f of a. That's not true for all values. It's only true at this specific value of x, which we're calling a in this example. It doesn't mean that every single x value has their y values equal to this. For part D, the line y equals f of a is tangent to the graph of f at x equals a. That's not necessarily true. The line y equals f of a is a horizontal. If the function had a horizontal tangent line, then yeah, that would be true. But if it's not horizontal, we'd have to take into consideration what the slope is, and this doesn't talk about the slope. And then last but not least, the line x equals a is a vertical asymptote of the graph of f. Again, unless this had a vertical tangent line, that wouldn't be true either. So taking into consideration that that's not guaranteed by this. The only thing guaranteed by it is that it's continuous. And that is the end of this video.